Good morning, everyone. This is going to be a recording that kind of goes through Monday, Tuesday, and hopefully some of what we've done on Wednesday. I just want to make sure everybody's caught up and has everything completed. So let's go ahead and take a look in Monday's folder. So this is from Monday, February 8th. And for this activity for today, it's mainly a review. So last week, we started talking about Newton's second law of motion, and that's kind of where we're going to continue for this week, starting on Monday the 8th. So let's take a look at our bell ringer. Here's our bell ringer. It says the forces acting on a skateboarder moving at a constant velocity along the sidewalk are shown in the figure below. Which of the following is the net force on the skateboarder? Well, remember that net force relates to the total complete force that an object will experience. And so the skateboarder is moving forward. It tells you right here he's moving at a constant velocity, so he's moving forward. And notice 35 newtons in the forward direction and 35 newtons in the opposite direction. So this force right here probably represents friction, for example. It could be rolling friction from the wheels or fluid friction from the air. But notice that they are equal and opposite. So that means that these two cancel each other out. So this direction, forward and backwards, the net force is 0. But we need to also include the information here. It says the normal force and the weight of the skateboarder. So weight is a downward force, right? So if you're sitting in a chair, standing on something, your weight is a force downward. So there was a downward force of 600 newtons. Then you see this term normal force. So normal force is basically the force exerted back upwards from the skateboard. But they're both the same magnitude, 600 newtons and 600 newtons. So they will cancel each other out. So that means that the total net force acting on this particular skateboarder is in fact 0 newtons. And that makes sense because he is experiencing a constant velocity, meaning he is moving along at a constant speed in a constant direction. So now that we've gone through that, the next thing that you need to make sure you do is to open up the Google Docs. It says Newton's second law guided notes. So here's the notes here that you will click and open up. And there is a corresponding PowerPoint. So you will click in the sections here to complete your notes. So we're going to look at review, speed, velocity, acceleration, deceleration, and then at the very end, there are also a few practice calculations using Newton's equation F equals m times a. So at the very bottom, if you scroll down, here is a PowerPoint that corresponds to that. So you're going to use this PowerPoint to fill in the blanks of the guided notes. So I'm going to get ready to pull up our PowerPoint, and I'm going to go through kind of a quick review. You have access to the PowerPoint. So if you need to go back and take your time to fill in the blanks, you can do that because you have access to it. So you should be able to download it here. All right. So everyone should see Newton's second law of motion. So this is the PowerPoint that goes along with the activity. So remember that the net force shows whether the forces on an object are balanced or unbalanced. Unbalanced forces produce a change in motion, and force is measured by what we call newtons, abbreviated with the letter N. Speed, velocity, and acceleration. These are three things we're going to continue talking about over the next few weeks. Speed is the distance an object travels per unit of time. So a car goes 50 miles per hour. Speed limit is 45 miles per hour. In the lab, or in some of our virtual labs we're doing, speed is going to be recorded using meters per second. That's our standard unit. What about velocity? Well, velocity is the speed an object has in a particular direction. It has the same units, meters per second, but you're also going to include the direction. So you would say the car is traveling 45 miles per hour eastbound. The car is driving 50 miles per hour westbound. So velocity is simply speed combined with the direction an object is traveling. And that's important in terms of observing motion of objects. We need to know, well, which direction is it moving? Lastly, acceleration is the rate at which velocity changes. We record velocity as meters per second squared, or m/s2. So let's look at the example down here. There's a runner. Okay, a runner would be set up on the track ready to run in a specific or particular direction in a certain lane of the track. And then when they take off or the gun is fired, they are going from an initial velocity of 0 because they're not moving. And so you would say that the runner accelerated from 0 to whatever velocity in a certain amount of time. So that is acceleration, the rate at which velocity changes in a specific amount of time. Movement, motion, and acceleration are always caused by unbalanced forces or a change in motion. Let's put it that way. A change in motion or acceleration is caused by unbalanced force. What are the differences between speeding up and slowing down in terms of acceleration? Well, accelerating is a positive change in velocity, meaning something is going faster. If it goes slower, you hit the brakes on your car to slow down, you are decelerating or experiencing negative acceleration. Remember that Newton's second law states that the net force is equal to the acceleration times the mass of the object, or F equals m times a is the specific equation. We can use this equation to determine F, the net force, in relation to the mass and acceleration of an object, or we can rearrange the equation and we can solve for mass, or we can solve for acceleration. So the units for acceleration are m/s2 meters per second squared. Mass is always recorded in kilograms, and F is the net force in newtons. Acceleration does depend on the mass and the amount of force. So let's look at the example here. There are two forces. They are the same, but one is being applied to a small object and one is being applied to a larger object, or an object that has more mass, like a car. So the smaller object will in fact move faster or accelerate faster than the object with the large mass, like the car. So the smaller the mass, the higher the acceleration. The larger the mass, the lower the acceleration. So let's compare two examples, a volleyball versus a bowling ball. They're about the same size, but clearly have different masses. So a volleyball with less mass accelerates quicker or will move more quickly than, let's say, a bowling ball, which has more mass and would accelerate more slowly. So if you had a bowling ball and a volleyball on the ground, imagine if you applied or pushed them with the same force. The volleyball is going to roll or start accelerating faster because it has less mass. Now, here are some examples. These examples are included in your worksheet that you're filling in, right? Or your guided notes. So what I'm going to do now is I'm going to stop sharing and I'm going to come back to the main screen and I'm going to share my camera with you and I'm going to work through these examples. So I'm going to start my video and I'm going to go through a couple of these examples with you. Okay, so there are 6 examples embedded in these questions. So I'm going to go through number 1. Number 1 says a baseball has a mass of 0.2 kilograms. If it accelerates at 40 meters per second squared, what is the net force? So remember, we're using F equals m times a. We have the mass, which is 0.2 kilograms. We also have acceleration, which is 40 meters per second squared, and we basically plug them in. So F is equal to 0.2 kilograms times 40 meters per second squared. And let's plug that in and see what we get. All right, so you should have come up with 8 newtons. So this is a force of 8 newtons. Let's try the next example, number 2. A 6-kilogram cat accelerates at 1.5 meters per second squared. Find the net force. So all we have to do here is erase our values, right? Because we're using the same equation. So in this particular example, it says that the mass of the cat is 6 kilograms. The acceleration is 1.5 meters per second squared. We're going to plug them in, see what we come up with. 6 times 1.5, and we get 9. Okay, so 9 newtons, if you want to plug this in here. Mass, 6 kilograms times 1.5. And there you have it, 9 newtons. Always remember to include your units. Okay, I'm going to go ahead and do number 3 because for number 3, we're rearranging things, okay? So for number 3, we're going to change it up a little bit. And number 3 asks us, suppose you pull a 10-kilogram sled, so the net force is 5 newtons. What is the acceleration? We can rearrange the equation. So now we want to solve for this. So A is equal to F divided by M. And now we're just going to do the same thing. We're going to plug it in. So A is equal to F, which is the force. And in our problem, the force is 5 newtons divided by the mass of the sled, which is 10 kilograms. Calculate that. Let's see what we come up with. So you should have 5 divided by 10. 0.5 meters per second squared. And let me make sure everybody can see this. All right, so again, all we've done is plug things in, but we did rearrange the equation. So anytime you see something that's asking for acceleration, it's force divided by mass, okay? And then you put your numbers in and you calculate. So now that we've done that example, we've done 1, 2, and 3 on the worksheet. I'm going to skip down to number 5 because number 5 is asking us to calculate the mass of an object. So now we're kind of changing things up. Again, we're still using the base equation, F equals M times A, but let's swap it up and we're going to use solve for mass. So M is equal to force divided by acceleration. Now let's plug it in. So we're doing number 5 on the guided notes you should be filling in. So for number 5, it says here, basketball is thrown with a net force of 9 newtons. 9 newtons divided by acceleration, which is 1.5 meters per second squared. And let's put that in our calculator. Okay, and kind of see what we come up with. So 9 divided by 1.56. So the mass of this object is 6 kilograms. Okay, so again, if you're solving for mass, F divided by A. If you're solving for force, M times A. And if you're solving for acceleration, it's force divided by mass. But all of these come from that base equation that we've been talking about. All right. Okay. So now what I'm going to do is I'm going to stop sharing my camera and I'm going to go back into Schoology. So at this point, I have done several of these problems. So you should only have 2 left to practice on your own. So now that I'm back into Schoology, and this is basically it for Monday's lesson. Make sure when you finish the guided notes, you submit. The next folder I'm going to go to is going to cover Tuesday, February 9th. So I'm going to click on that now. Again, we have a bell ringer and we have some practice calculations. So click on the bell ringer here. And let's take a look at our example. Use the formula and the diagram to answer the following questions. Force is equal to mass times acceleration. Akbar applies a force of 50 newtons. Lucia applies some force, and the object is 10 kilograms. says Akbar and Lucia apply opposing forces on a wheeled cart that has a mass of 10 kilograms. The cart accelerates toward Akbar at a rate of 2 meters per second squared. What is the amount of force applied by Lucia? Well, we want to know just her force. She is pushing here. So let's take a look. What is her net force? How much can she apply? Cart's 10 kilograms. And the cart is moving towards him at 2 meters per second squared. So we plug that in. F equals m times a. F equals mass of 10 kilograms times the acceleration. And we end up with a force of about 20 newtons. So the correct answer for this one is, in fact, A. Okay, so now that we've gone over that bell ringer, let's take a look at these practice calculations. Most of what we're doing for Newton's second law, the bulk of it is equations, and then looking at speed, velocity, and acceleration. So when you click on this document, it's going to come up as a Google slide. There are 2 pages total, page 1 and page 2. There are 10 questions. Your job is to go through each of these, click on the box and type in force, click on the box and mass, and then acceleration. So basically, you're going to work through these problems and you're going to be solving for force, mass, and acceleration. You click on the box, type in your answer, then you're going to submit it. So what I'm going to do is I'm just going to pull a few random problems like I did a few minutes ago, and I'm going to come back to my board and I'm going to work through them with you. The rest of the problems you are responsible for completing on your own. So I'm going to stop sharing this assignment for Tuesday, and I'm going to come back to my video. All right, now let's pull some examples from Tuesday's calculation worksheet. So the examples I'm about to do are from Tuesday's assignment. Okay, and I'm just going to kind of randomly pick some to go over with you guys. You might have to zoom in a little bit so you can see the assignment, not a big deal. Usually if you put it on 100%, you can see. So let's go ahead and do number 1, because number 1 is a traditional calculation. So again, we're working with F equals m times a. Number 1 says, what net force is required to accelerate a car at a rate of 2 meters per second squared? The car has a mass of 3,000 kilograms. So we are looking for force. So again, this is number 1 on second law practice in Tuesday, February 8th folder. So the first thing we want to do, we know what the mass is. The mass is 3,000 kilograms. And you are typing this in. We also know what the acceleration is, 2 meters per second squared. Then we need to find the force. So F equals m, 3,000. Times 2 meters per second squared. So 3 times 2, that's 6,000. So we have now applied a force of 6,000 newtons to that particular object. Okay, or that is the force required to accelerate a car at that rate. All right. So that was number 1 on the worksheet, practice. Let's take a look at, let's see, number 2, if you're working it out. Number 2, you're also using force equals mass times acceleration. You were given mass, you were given the acceleration. You plug it into the equation and you solve. So number 2 is similar to this. Okay. Number 3, again, F equals m times a. You are using the same equation for number 3. And if you look at number 3, you are given the acceleration, 5 meters per second squared. You are also given the mass. It's asking for the force. So for number 3, all you do is plug in the mass that you're given in the acceleration, solve for the equation. I'm going to skip down to number 4. So now I'm going to do number 4, excuse me, from the worksheet. All right, so number 4, So remember, your base equation is always F equals M times A. However, depending on your scenario, and I know you guys can't see I wrote that too high, depending on the scenario or the situation, you may have to change the equation around. It depends on what you're solving for. So for number 4, they want to know what the mass is. What is the mass of a falling rock if it produces a force of 147 newtons? So to find mass equals force divided by acceleration. Now the problem tells you the force. In this problem, it says the force is equal to 147 newtons, but it doesn't tell you the acceleration. So what I want you to focus on in this problem is the fact that it tells you the object is falling. What does that mean? Anytime an object is falling on planet Earth, this is the acceleration. A is equal to 9.8 meters per second squared. So highlight, underline, circle, asterisk. Anytime an object is falling on planet Earth and it is experiencing little to no air resistance, the acceleration is 9.8 meters per second squared. That is standard, okay? So now that we know this, plug it in. Mass is equal to force, 147 newtons, divided by acceleration, 9.8 meters per second squared. We're going to solve it. Again, I encourage you to use your calculator. Don't try to do all this in your head unless it's pretty simple math. 147 divided by 9.8 gives us 1.5. 1.5 kilograms for number 4. So 147 divided by 9.8. Oh, excuse me, 9.8. Typed it in wrong. See, always check your math. 15, 15, 15, excuse me. Apologize for my mistake. That's 15, okay? 147, check again, divided by 9.8 is 15 kilograms. All right? All right, so I'm going to pause right there. And I'll have to come back to you guys in just a minute. So let me pause this and I'll come back and finish the next example. All right, so we just finished number 4. Now let's go back and look at the second example. So for number 4, we were calculating the mass of an object. Let's do one more example for number 5. So number 5 says, what is the mass of a truck if it produces a force of 14,000 newtons while accelerating at a rate of 5 meters per second squared? So again, if you're solving for mass is equal to force divided by acceleration. We're given the force and we're given the acceleration. So the force is 14,000 newtons. And the acceleration is 5 meters per second squared. We're going to plug those in. So mass is equal to 14,000 newtons divided by 5 meters per second squared. So let's plug that in. All right, so once you plug those in, you should have 14,000 divided by 5 should give you 2,800 kilograms. All right, so that's number 4 and 5 we've just did. Let's do one more example. So on the second page, you'll find number 6, 7, 8, 9, and 10. And at this point, we're going to transition to solving for acceleration. So we're going to rearrange our equation and we're going to do one of those examples. So let's go ahead and do number 6. So for number 6, you're solving for acceleration. So A is equal to force divided by mass. So that's how you'll set the equation up to solve for acceleration. And if we take a look at our problem for number 6, it tells us that the mass of this particular object is 0.5 kilograms. And the force acting on the object is 25 newtons. We're basically going to plug that in. A is equal to the force, 25 newtons divided by the mass, which is 0.5 kilograms. Let's plug that in and solve. And you should come up with 50. Specifically 50 meters per second squared. Okay, so the remaining problems are very similar. So again, if it's asking for force, you're going to use F equals m times A. If it's asking for acceleration, A is equal to force divided by mass. And if you're looking for mass, mass is going to be equal to force divided by acceleration. Okay, so make sure you always put your units, otherwise the problem would not be correct. Okay, all right, so that takes us through the rest of Monday and Tuesday's material. So you have everything you need to submit your work and get your assignments done.